Welcome everyone to today's webinar, Taking Your TI-Nspire CX II CAS to the Limit. Leading today's session is Mr. James Mott. He's Head of Mathematics at Southern Cross Grammar. He has a passion for technology, particularly in how it is used to enhance student understanding of mathematical concepts through visualizations. So, good evening, James.
Good evening.
As our time is limited and I don't want to drive anyone crazy, sorry, I'm just trying to integrate some jokes here. Let me switch over to James.
Excellent. Thank you, Peter. And that's, I think that's quite a hard act to follow. Unfortunately, I don't have any jokes in my back pocket, but we'll see how we go. So as was sort of described in the session tonight, like it's sort of a look-see of how we can use the technology to tackle some calculus-related exam-style questions. And we'll look at both differential and integral calculus. And I guess the main thing that we're trying to get here is that hopefully you guys walk away with a new idea or a new trick that you can use in your classrooms and convey to your students. And if you do have any questions, please feel free to type in the chat, unmute yourself, shout out. Personally, I want you guys to ask questions. And as I say, most workshops, the more you give, the more you get out of the workshop. So please really encourage you if you've got questions to ask away. So first up, I guess a sort of a common question that's appeared in some past examinations. Here we've got this log graph, and we're told that we've got this tangent to the log at x equals 2, and this tangent passes to the origin, and we want to try and find this value of k. Now, as I'm sure we'd all do in the classroom setting, we'd encourage our students to try and visualize this information because kids can get overwhelmed with what's presented to us. So hopefully they would do some sort of sketch like this on paper to get a sense of the information that we're given here. So we're going to point at 2, and we know that it passes to the origin. So because we're looking at the tangent line, what we can do is actually find the tangent line of our curve. And if we've not seen that one before, if we go to menu, we are looking at some calculus. So we'll go to the calculus sub-menu, and there we've got our tangent line command that we can use. Now, in order to use this, we first need to enter in our command, or so our function. So our function in this case is the natural log of kx minus 1. So natural log k times x minus 1. And now we need to tell the commands at which point we are interested in. To do that, we'll put a comma in and type in the point x equals 2. There we're telling we want the tangent line of this function at x equals 2. And that'll give us the line in the form y equals mx plus c. Now from that visual plot before, we know that pass to the origin. So ideally our y-intercept here would be 0. So now we can solve for this particular expression. So we could type it in or use our earlier work by pressing enter to bring it down to a new line and just getting rid of it. And we want our y-intercepts to be equal to 0 and solve for k there. Now, another thing we can also talk with students about is why is it that we didn't really need to define our function? Because often we do encourage students to define stuff. And the conversation can be had, well, because we're really only using that function for one calculation, just for efficiency's sake, we don't really need to define it. If we're using it multiple times, like perhaps subbing in value or doing something else with it, it might make more sense to define it so we can use it more effectively on recall. But for a one-off calculation, you don't really need to worry about it. Alrighty, in this one here, we've been told that fx is this lovely cubic and h is some sort of inverse of this. And we want to try and find the derivative of h at x equals 1. So first up, we'll define our function. Now I've defined it by using the assign command, which we'll touch on in a little bit. Depending on your students, you may want to use the define command. Menu actions define. Otherwise, we can use the assign command for a bit of efficiency, and I'll do that in a little bit. So first up, we want to try and find the inverse, and we can do that using the technology. So what we can do is use the solve command. And if we think about how we want to find our inverse, we'd interchange x and y. So in this case here, we can say x is y, and solve out for y. There's our inverse. Now from here, we can then define that as hx. So if we want to define that, h of x, and we can define using the assign command. And to use the assign commands, we can press Control and that template button just underneath delete there in red. So it's a shortcut way of defining something. And we want to define our earlier work, so we can highlight it, press Enter to bring it down, and just get rid of that y equals there. Now we're all good to go to try and find the derivative at the point x equals 1. And once again, we can do that pretty efficiently by relying on our calculus menu. So we've got our menu, our calculus subsection, and our second option is what we want, the derivative at a point. So here we're working with x. We're interested at x equals 1. Then we can press OK from there. All we have to do is look at our derivative of h at x equals 1. Now, what can also pop up potentially in sort of a multiple choice scenario is when we may be given the graph of derivative and then asked from there to try and find the graph of the. So what we can do is to try and ask students to think about what kind of curve may best represent the graph that we're working with as a approximation. Now, off the bat, this one's a little bit tricky to see, but it kind of looks like a quartic. We might start with a nice basic case here and then build it up from there. So what we can say is that we might have some sort of turning point at perhaps x equals -1 or 2, and then maybe 2 x-intercepts from there. On the graphs page, we could try and play around with building up this function. So with a quartic, we might have a turning point, say at x equals 1, then our 2 x-intercepts for 2 positive x-intercepts there. Kind of looks like what we've got to work with, but not just, because ideally our graph is just a little bit more translated. So we can put in some sort of translation from there. And we might say, let's move it up by 1 and see what happens. That's kind of a better looking graph to the one that we've got in the question to work with. Now, the benefit of doing this is we can say to ourselves, well, in that graphing template, we can actually sketch the antiderivative based on our question for F1. So we can enter in an antiderivative into this template by selecting our template button just select our antiderivative template. Now, because we've got the graph of F1 defined in blue there, use that sketch the graph of its antiderivative. So that should give us a rough approximation to what the graph looks like and knock off a couple of options there. And likewise, we may be presented with some questions whereby we might be given a function and then asked to find its derivative. And in a similar sort of process, we can get the students thinking about, well, what kind of curve does that look like? In this case here, it looks like a pretty nice log function. So once again, we can start with a log function and see what that looks like. So we had an asymptote at x equals -3, so +3. And just like before, as we can sketch an antiderivative from using the template, we can sketch the derivative using the derivative template. Sketch f1 of x to go. And now here, it would be a great opportunity to have a conversation with the students about why is it that we've got this red part of the graph over here, despite the fact that the blue graph isn't there. Or in a more sort of formal way, why is it that technology is showing the graph of the derivative here, but yet the graph of the original function? So we didn't need to be mindful of the domain. And again, visually, we can sort of see where the domain would be. But if the students still aren't quite understanding, we can then talk about the domain of the original function. And from the graph that we saw in the question, our domain was for when x was bigger than. So we can put in that domain restriction. And that'll also update the graph of the derivative. So if you've got questions all throughout, please feel free to ask away. So the question that we have here is, I guess, an age-old classic, perhaps from 11, but also maybe year 12 as well. We've got a rectangular sheet of, in this case, metal, a width of 20 and a length of 60. And we're cutting out some corners from all the corners. And folding up the sides to form a box. And ideally, we want to try and find the maximum possible volume for this box. So first up, we would need to define some sort of expression for our volume. And save a bit of time, there would be our equation for our volume. Now, in a normal sort of fashion, what we would do is to try and find our stationary points. So we may decide to solve for when our derivative, zero, and we can obtain that derivative template just from that template button to save time. Solve the derivative of Vx equal to 0 for x. And then from there, we'd ask students then sub in those x values to find the corresponding volume or in any sort of general. Now, that may take a little while and it may take a couple of keystrokes. But what we can do, and particularly in this case with multiple stationary points, is we can do it all in one line using some simultaneous equations. So if we were to go to menu, go to algebra, and rather than solve, we're going to select solve system of equations. First one we'll do there. And if we think about what we've just done step by step, first up, we were trying to solve the derivative equal to 0. First line, same old. Now, if we think about the output that we got, those were just some x values. So this line here, oops, first line, that's just going to spit out some x values for us. Now, thereafter, we then sub in those x values to obtain our corresponding y values in this case. What we can do in the second line is type in y equal to function Vx. Because what's going to happen is it's going to take those x values, sub them into here to get the corresponding y values. And you might be wondering, why are we doing all this work for simultaneous? Well, if we look at the output now, that's how it's giving the x value with the corresponding y value there. Now, I admit the numbers aren't quite nice, so we might just look at the approximate. But the main message I'm trying to emphasize here is that by using some simultaneous equations, it's pairing the x and the corresponding y values together. So it's giving the output kind of like a coordinate, the corresponding x and y together, as well as that second one there as well. So we can do it all in one line, reduce the amount of keystrokes, a bit more efficiency, and our answer in a nice. What can happen is students may some keystrokes, type in the wrong thing, bring down the wrong thing, sub in the wrong thing, do it all in one line. It's more advantageous too. Now, we can, I guess, generalize the problem from here. It may look quite familiar to some people. But in this case here, we're now considering what happens if this sheet of metal now has a width of W and its length is now 3W. before, and as before, we're going to try and maximize the volume of this box. So again, we need the expression for our volume, which is and once again, we can do the exact same thing to obtain our solutions in terms of W. So once again, we're going to rely on our simultaneous equations, or in this case, system of equations. First up, we're going to solve our derivative of dx equal to 0, and then sub that into equal dx. We get our solutions as nice ordered pairs. And again, looking at this, it's not quite obvious which one we may accept, which one we may reject. So we might just have to rely on some approximate solutions to see that. At first, it's not quite okay because we can't really have it. We might have to reject that first one and accept that second one there.
Now, just before you go on, sorry to interrupt there, James.
Yep, no, you're right.
John. There's a lovely TI-Nspire file which I can share with participants. If it's all right with you, I'll see if I can share it from my computer. So hopefully participants can see that on their screen now. So this one wasn't created by me. I'm just really envious of its creation. Now, I still encourage teachers to have students physically create the box. I'm not sure about you, James, but I still like the tangible aspect of that, where kids cut the corner out, fold it up, we collect some data over the height of the box, and the kids measure the volume, and we draw a scatter plot, and then they come up with the equation. I think it's important because a backstory of that was I had one. I didn't draw little dotted lines for the kids to measure, and one of my students many years ago wanted to know what height he should be measuring to work out the volume. And I didn't understand his question. What do you mean, which height? And eventually I got to the point where I realized he didn't cut squares from the corners. He didn't understand that you'd have to cut a square from the corner. So making the physical box is a good thing to do, because if the students don't understand that you've got to cut a square from the corner, otherwise the ends of your box end up taller or shorter than the sides, which is kind of silly. So this lovely diagram has got some beautiful animations in it. So we can fold up the original box, which is quite neat. We can also have a look at this graph over here. Now, at the moment, the result is actually hidden. So you're probably wondering what's the story behind the graph. But the other thing I get the students to do is they have to nominate where they think the maximum volume will occur. And kids tend to go about there somewhere. And it's interesting, I think that kind of stems from the paddock problem that a lot of people have done, perhaps as the precursor to this, where they're working out the maximum area of a paddock, and you've got a river bound on one side, etc. So you've got 3 bits of fencing, and yeah, I think that's where they're getting this idea from. It's going to be a square or whatever. So when I click on show over here, we can see we missed the maximum volume by quite a lot. It's quite surprising for some that it's all the way back there. So the box is actually relatively short. And there's various reasons why that might be, and I won't take up all your time mentioning those. But it also then leads into another lovely question, and that is there some sort of an original template, piece of cardboard, sheet of metal, whatever it was in the question, that would create a maximum volume that is a cube? So in other words, we can see that this rectangular box is a lot shorter than it is wide or long. So is there some sort of a shape that we would start with that would mean the maximum volume would occur when it's a cube? And there's lots of other maximum volume type problems. And if you're looking at a calculus one, get a motion sensor, a CBR2. I did this one as a rate of change problem with students, and we got a 100 centimeter balloon, as in a really big balloon because it's spherical. I had one of the students attempt to inflate it. I think he played bagpipes and he struggled to inflate the whole thing. So always good to bring in a bicycle pump or something like that and inflate it. And then what we had is the motion detector aimed at it as we released the air, holding the balloon steady, and you get a lovely, I won't say whether it's a straight line or a curve, but you do get a graph of the rate at which the radius is changing, which is kind of cool. And then we did the calculus attached to that. So lots of lovely calculus problems there that you can try with your students. But I'll put a copy of this file because I just think it's really well done. It's in Nspire, and the difference is we're on document preview, not handheld preview. So using the software to illustrate a concept that you may be teaching in class. All right, well, I'll pass it back to you, James, to finish off some more of those questions on calculus.
Thank you, David. I mean, I'm keen to get a hold of that file, and I think in particular that'd be a nice activity, like the physical aspect you mentioned. That'd be a really nice one to do with, say, year 9s or 10s, depending on your curriculum. Yeah. To get a hands-on approach to it at the beginning.
I'm not sure if everyone's seen Joanne's comment in the chat there, creating a notes page for maximum minimum problem. Have you got a minute perhaps to show what Joanne's talking about? Maybe drop in a new document.
Absolutely, yeah.
Function and show them what Joanne means by it. It's really powerful, absolutely, using the notes page for maximum minimums.
Yeah, I'll just take a slight tangent. Again, pardon the pun there.
Oh, nice.
And talk about Joanne's point there. So, I guess to preface this, all my work at this stage has been in a calculator page, but if you're unfamiliar, the notes page is a far more powerful environment that's dynamic. So if you want to add a notes page, now we can perform some mathematics in this. And to do so, we would need to insert a math box. The shortcut there is Control-M. And as we're doing a calculator page, we can find a function. So might go with fx, and I'll find that as, see if this one will work, x cubed x. And then if I want to then find some stationary points, I can then, as before, solve. All the commands are hidden underneath the calculations section here. Solve, if it does everything that a calculator page normally would. I guess what Joanne is getting at there is that the reason why it's so powerful, because there's a dynamic environment, all these boxes are linked. So if I were to change my function, say an x squared, it would then subsequent calculations that. So theoretically, create document with all your commands set up. So whether it be stationary points or using fmax, fmin, whatever it may be, average rate of change, whatever you have in mind.
Now, can you do me a favor? Now, I haven't tried this one when there's multiple answers, but just go down into that last maths box, that's the one, and type in left and then open bracket, and we should be able to just use answer, ANS. Otherwise, we'll try it on the original thing. Yeah, press enter. No, it doesn't like it from there. So click OK on there. I didn't think it did in the notes application. I know it does elsewhere. So just delete that text, because we can actually pick up part of an answer. So I know some people use zeros. I see Chris mentioned in there he used zeros. Maybe show the zeros option in there as well.
Yeah, of course.
That works neatly.
So if people are unfamiliar with zeros, in our menu, normally we'd use solve to solve x or whatever after, but we can also use the zeros commands. And the manner in which this works is, whichever kind of expression we type in, and if I insert a comma x, what this command zeros is doing, it's equating this whatever expression we put in here equal to 0, and then it'll spit the answer out as a list. And depending on what we want to do, it can be quite powerful. And I think what Chris might get at here as well, or might suggest or might be shouting from the other end of the screen there, is that with that output, we could then substitute that output into whatever function we make. So as a list, we could define this, define it as some x values. I could potentially sub that into my function f to get my corresponding y values then. Does anyone else have any other questions at this stage relating to like what we've seen so far, or maybe what's on the screen so far?
No, I think we're pretty good so far, James. The only other tip I typed in, I'm not sure how many people saw it, was James has been using the menus and obviously the templates. There's some shortcut keys in there as well. As James mentioned, Control M for a maths box, but also Shift and minus will give you the derivative sign, which is great for calculus. And obviously Control Escape or Control Z if you wanted to undo that. And yeah, Shift and plus will do the integral sign, which is kind of cool.
Alrighty.
And Chris came back and said, yes, that's exactly what he does with the zeros.
Yep. Alrighty, so the question in front of us here is I guess a common question that's popped up in a few past exams, and a question or a concept that's quite tricky for students. So first up, we're told that this definite integral from -2 to 6 is equal to 16, and then some sort of transformation has been applied, and often students don't view this as a transformation. And then based on this, we want to try and find out what the new definite integral would be. Now, what we can do actually is encourage students to approach this from a graphical perspective. And we can sort of lean on the idea perhaps of average value. So how we can view this particular definite integral here is that we've got a width of 8 going from -2 to 6. And we know that of a rectangle, width times the height will give us the area. So 8 times 2 should give us 16. So the choice of the function fx is completely arbitrary. It can be anything it wants to be in a way. But to make our life a bit easier, we can view it as a rectangle. And if we do, what we can do is actually sketch this thing, say that we've got this function that's 2, and I've sketched it between -2 and 6. So the area under this particular line here this would generate a rectangle, whose area would be 16. And for the viewers at home, I'll just confirm that as well. I'll just put in a point just to make this work a little bit neater. So point at -2 and at 6. And then the Nspire has a built-in feature inside the Analyze graph. It's got a lot of lovely features here. But the one I'm going to use is integral, which determines the area underneath our graph. So I'm going from -2 to 6. And thankfully that matches up with the 16. So there's my rectangle. Wondering, well, where are we going with this? So again, I'll flick back to the other screen, the question. So now we're looking at this transform function, 2 bracket x minus 1. Now, because we've sketched the graph of 2, that's our fx, we can apply those transformations to our function f1. So f1 is defined as 2. Then if I just simply type in our transformations, 2 bracket x minus 1, I've now got my transformed curve. Hopefully, we can sort of see this graphically that the area should be 2 times 4 to give 8. We could go through the whole song and dance again to plot some points. But really, by using some rectangles as our curves, it just makes it so much easier for students to engage with such a question. It doesn't matter whether I choose the red curve or the blue curve, it's the same y value. And there we can see that the area is going to be 8. So again, we can sort of view these questions more as a transformed rectangle, or again, you can lean on the idea of average value, or perhaps rewrite it as an average value, divide both sides by 8.
Sorry, James, you already cut out a little bit there.
Oh, sorry.
Here's a question without notice. You're going to love me for this.
Yep. Go on.
I did explore that same question, and I can see, students might go, well, does that always work? And absolutely, I'm the same with you. It's an arbitrary equation, therefore it should work for all equations. So to further convince students, and not that 2 examples says it's true for all, absolutely not. It's not proof by induction here. So what if we said to the students, suppose our original equation was an x squared, a dilation of x squared. So if you want, drop in another application or another problem, and let's define it as x squared, or a times x squared. So you might need to, sorry, I'm sort of doing it as I go along here.
No, you're right.
Yep. And of course it won't graph it, and it'll prompt you for a slider, which I don't actually want the slider, but you could put given a equals 2 or something like that, and we'll figure it out in just a moment. So a equals 2. And we don't need a slider because we've defined it. Now, we don't know that the area between -2 and, what was it, -2 and 6 had to be 16. So put a calculator application in. And what was that? I think it was F3, wasn't it? So we really want to solve the integral from -2 to 6, I think. Yep. Of a, let's do ax squared because I think it'll pick up the stored value for a there. So a times x squared. The x equals 16. Solve for a. So now we've got a value for a, which we could substitute into our graph on page 9.3. I'm impressed you memorized what it was. I didn't.
Might just make it a bit easier. Rather than subbing in like that, I might just replace a.
Just type it in. There we go. And now you could do the integral between -2 and 6.
Oh, sorry, yes. Let me just put the main restriction in. So we get the bit that.
Now you can type the numbers in there as well. It'll accept that. So we've confirmed that our solution worked, and now we could do the integral between 0 and 4 and see that we also get 8. So we've got a different curve for f of x, and show that our integral between 2 and 4, that's the one.
Four, and you said we can type it in, so let's try and minus 2.
Type in 0.
Oh, sorry, 0, my mistake.
Yep.
Type in 0.
And 4, I think it was. And you can type in 4, yep.
There it is.
And we get 8. So we've shown that, we've created 2 different functions. I'm thinking, I put the question out there to people to say, well, how well do your students do on this sort of question? So we've shown them a workaround, but I'm thinking it'd be kind of cool to have an activity whereby it's showing the area and we're manipulating with the original function, and then they're experimenting around to get the areas that we require. In other words, dilate these points, because that's really what we're talking about, isn't it? How we're doing a translation and dilation of the terminals on the integral. So I'm thinking there's an activity screaming out there to help students understand it rather than working around.
Yep. Yeah, nice one.
All right, back over to you, sir.
Righty. So here's a question whereby, and I guess now it works on parabolas, we're looking at parabolas once again. Graph 2 minus x squared. And we're told that the region of A there, same as the region of B, so these 2 areas are equal. that in mind, we want to try and find the value of k. So as we would expect students, do think about what kind of info we need first. So ideally, we want to know that x-intercept. So if you've got students who can't quite see it, ask them to solve to get our x-intercept and use the graph to inform which one we really want to take. Leave one there. And because we want these two areas to be equal, ideally we want the expression for this area to be equal to the expression for this area. So we can enter in those expressions. First one, going from 0 to root 2 of our fx, the x. And because the area is below, we want to put in the negative area from of and solve that for k. Now, what can often happen when playing around with integrals and solving equations with integrals is the Nspire may occasionally spit out some multiple answers for. So it is really worthwhile getting students to refer back to a visual or a diagram or even a question to help them interpret which solution to take here. Based on our graph, as before, we can see that k is going to be 6 there. Now, this question here, again, may be a bit familiar to some people from a few years ago now. We've got this function, the domain of 0 to 4 inclusive, and we have this parameter k in here. And the question is, for what values of k would we have a minimum? Students can be really confused by this. I guess almost a throwback to the very first question is just encourage them to visualize it. So with this particular question, we can sketch it. And I guess to sort of reveal what's going behind the scenes, I've just typed in my function, my domain restriction between 0 and 4. And then as we sort of saw before with that parabola, if we do have a parameter in there and press enter, it'll prompt us for a slider. And that's exactly what we want. Now, we are interested in the minimum. So once again, we can lean on the technology to help us identify where the minimum is. Now, I want my lower bounds to be 0. So I'll use P as suggested before in terms of typing in 0 for my lower bounds. And then my maximum was my endpoint. It says my minimum. And then if we were to vary the parameter k, we see that minimum is going to change depending on what k is. Now, just in a basic sort of visual sense, we can sort of see that 2, we've got that minimum at 0. And if we keep decreasing k, that minimum is still there. So already just leaning on the technology with these sliders and so forth, the students already have an entrance into the question to get a sense of what it is they're visually trying to determine here. So straight away, kind of looks like 2 is a starting point, and anything smaller than 2 is going to look pretty good, because anything more than 2, that minimum is no longer at 0. So now we can sort of then begin the conversation with the students. Well, what do you notice about the curve for values of k2 or smaller than 2 at the point x equals 0? So ideally, for the minimum there, we would require that, assuming this curve kept on going, we would require the gradient there to be 0 or perhaps positive to ensure a global minimum or an absolute minimum. So what we can do is, as before, we can define our function. Now, I guess purposely, I've used a different problem. I mentioned this throughout as well. Each of these sort of problems here, you notice 11.1, 12.1, 13.1, it's just so that my parameters don't conflict between the graph and the, I guess, algebra I'm about to work with here. I've opened up a new problem rather than opening up just a brand new calculator page, because k is already defined here. And because I'm working algebraically, I kind of don't want that value to carry over. So we can insert a new problem. And to do so, we can press doc, insert problem there, okay, just to ensure that. So because I want the derivative at 0, once again, I can utilize the derivative at a point feature in my calculus menu. I'm looking at the point x equals 0, and I'm going to look at, straight away, I've got an expression for my gradient at 0 in terms of k. And ideally, just based on my visual here, I want this to be either positive or perhaps about 0 there, just to get that minimum turning point there. So we can solve our expression to be greater than 0, k value. However, we need to keep in mind what the restriction of k is. So the question, k was between 0 and 8. Ideally, values of k, 0 and now we could potentially refine the slide to be a little bit more granular. If we were to do that, we could right click on it. On the handhelds, it would be control menu, go to settings, and then perhaps change that step size. Maybe we just want it as 0.2, just get a bit finer detail. See there that it's still going to be strictly increasing in a positive slope. So that's about it, all that we had for you tonight, guys. Hopefully you've taken something away from that. And really, I want to give you guys this time and opportunity to ask questions about anything that you've seen tonight or anything that, any sort of questions you inspire.
Just
if you have questions.
while we're waiting for those questions to come in, James, I've got two things I want you to try for me. Just go back onto your graph application there. A lot of people don't really think necessarily about drawing the same function twice, but there's a reason why I'd do that. So I think on this, I'm not sure whether it's this page or problem 13.1, just jump onto page 13.1 there for me. Now, did you have a graph on that page, or there's no graph on that one on the following?
No, I didn't have a graph on that page.
Okay, so go back to 12.1, sorry, my mistake. And just tab up to the equation editor. And I think you've got it defined as f of x, haven't you, this equation? Now, have you got any domain restrictions on that? So that one's got a domain restriction. So now do f2 of x and just make that f of x.
Is that what you're suggesting?
Yep. Have you got f of x defined, presenter?
No, it's a brand new problem with that one.
Oh, okay. All right. Well, let's just put the quick way, of course, is going to be to just copy part of that f1 of x out. So that's it. Copy that and paste it back into the previous one. Control C, Control V, all those lovely tools, and get rid of it. That's it. Nice. And then change that to a dotted line. So that's a control menu. If people haven't seen it before in attributes, changing that.
Actually, I'll go a bit slower. So
yeah,
right click on the curve, attributes, change that from continuous to.
Yep. So the reason why I think that's worthwhile, now this is not something a student's going to do in an exam, but if we're using this as a learning tool, highlighting the importance of the domain restriction and getting students to understand that we have a minimum over the domain that we've been provided, but with not over the function, because some students might sort of go, well, why aren't we just calculating the derivative equal to 0? What's going on? And if you change the value of k now, then students will see that, I guess we'll call it the limiting case, for want of a better term, is when the actual turning point is sitting on the y-axis. And that's why we're able to do it at that. Does that make sense?
Yeah, that's a lovely point there, Peter. That like, whilst I guess we're talking about efficient use in exams and so forth, but ultimately this is more of a teaching tool, and we would, these conversations we have with the students beforehand.
Yeah, and I noticed someone else has just sent in, it's worth doing a split page. We can do a split page in a moment. If you want to bear with me for another problem though, insert a new problem. And people will notice that the page numbering, of course, changes.
So this will now be
in the graph application. Now let's just put in a nice simple function like x squared, because we mentioned using this as a learning tool before. Now this is just on the fly, folks, so I'm giving James a hard time here. Now a lovely shortcut on the CX2 is you can just press P to do a point. So either on the handheld or your computer, you just press P and we'll do point. And then when you hover your mouse over the function, it'll give you the option for point on. So that's nice. So click there and then just press escape so we're not creating any more points, and drag our coordinates away somewhere. And what I want to do, let's store the X coordinate in A. So we right click, which is control menu, and select store. And and then just put it as A. And now let's graph the derivative function. Tab, derivative of f1 of x, and then do a domain constraint. Yes, sorry, I didn't get the commands out. So double click on the function so I can edit it again. And just do the domain constraint for x less than a. That's it. So now, as you drag the point, we progressively see the derivative function growing. And of course, we could put a tangent to the curve, measure the gradient of the tangent, that sort of thing. It works really well with things like a sine function, so you can stop and pause at certain points. So the students actually see the derivative function being, because sometimes when it just all happens, there's too much going on at once and the kids don't necessarily make sense of it. But gradually seeing it, and the trick was to actually store that value, the coordinate, in A. Yeah, see, there you go. It's even simpler again, isn't it? It's nice and neat. And the beauty of that is if you change your original function, your parabola, to say, yes, we're in radians, so that's good. So you could change that to say sine x. That's it. So it's very dynamic.
Looking curve.
Yep. And then if you want to, let's change the domain. So let's click on the x coordinate, the x max there on the actual graph. Sorry, on the Windows settings. Yep. So let's maybe change that to a 2. Press tab. Yep. And let's say 3 pi. And -2 and maybe negative pi or something like that. And now click on the X scale and change that to as in the 0.5, sorry. Change the 0.5 to, let's say pi on 2 would be sensible.
Good.
And something that people might not know is if you now change the attributes of the X-axis, so right click on it, that's nice, isn't it? It's beautiful. Yep, right click, attributes, and then arrow down to the third one. And I think from memory, arrow to the left or the right. My memory didn't serve me well enough.
Hidden, shown, or...
Yeah, keep going one way because it will show. Oh, I know why, because the Y scale is too busy. So change the scale on the Y axis to say 1 would be sensible, or 0.5. And now do the same to the attributes on the X axis. That's it. So I'm not sure how many people realize you can get the entire scale drawn up, but it doesn't show up if it means that it's going to be too busy. So we can see the key points on the graph when it's, and I like the way that it gradually progresses as you drag that point across.
And sort of off the top of my head as well, this would be a nice one, even though it's not related to tonight's topic, but also for inverse functions as well.
Yeah, that's right. Exactly the same process as what you're doing there for the derivative of a function. Then as long as you store the coordinate, the x coordinate. The other thing I have done, and people can experiment with this, I've put the point on the x-axis. So say, for example, if I'm going to draw a tangent, it's really hard to control the rate at which x is changing when when the point is on the curve. So experiment with things like putting the point on the x-axis, and then you do construct a perpendicular line to pick up where it hits the function, and then you can drag the x value so you can get almost a constant rate of change, whereas you'll find it's really hard when the point is actually on the function to get a constant rate of change, because it kind of accelerates, if you like, as you sort of drag it across. I'm just checking the chat. We haven't got any other comments.
Yeah.
The only other thing,
I might just talk about Neil's point there in the chat from a little bit earlier with one of our good friends. Neil suggested that we can on the one page have both graphs and some sort of calculation environment there. And with any sort of page that we have, if we were to go to doc, page layout, you may notice even that little icon there, it's a little bit busy, but we can select what kind of layout we want. So we could potentially have a graph side by side with some sort of calculation environment, or perhaps top bottom. I kind of prefer a left right myself. And then we can insert like a calculator or a notes page and have a graph and a calculator page working side by side there. So we've got this one. So that's f1 of x, and again, notice how that's emboldened because it's using this definition here. So like f1 at 0 should give me
now we haven't got any more questions in the chat, but let's give them some homework to do. Now there's also a lovely way to ungroup there. I don't know whether you know the ungroup. I can't remember off the top of my head whether it's Control 6 or Control 4.
Yeah, it's one of them. So yeah,
for those if it doesn't work, we know we've got it upside down.
Yeah, there is a shortcut for the grouping. As Peter said, it's either Control 4 or Control 6. There we go, Control 6 ungroups.
And all it did is put the other application on the next page. Let's just try something else. So go back to page 14.1. Now we hid the coordinates. We didn't delete them. It's important that we didn't delete, because otherwise we can lose our value of A. So go on to menu and actions and hide show. And we can see, where did your coordinate go? I don't think you deleted it, did you?
No,
we can always just get it back. That's it. Nice. Now, this is what we'll call it positive and negative. So I want you to write the text on the screen that says positive. So, yeah, text, and write the word positive. Oh, Chris has just put a nice thing there. 6 is bigger than 4. To remember as makes page larger to ungroup. Okay, there's a mnemonic to help us remember. And now type in the word negative. So I'll add some more text. Now, we could put equations and all sorts of stuff here. I'm going to keep this really simple. So at the moment, we know the x coordinate of our function is positive. So now, right-click on the word positive and select conditions, number 9, and say a greater than 0. Now remembering a is the value that we've got there. So a is positive. Now, drag that to the left and look what happened to our word positive. It disappeared because a is now negative. Now, that's just the x coordinate. What I want people to think about, and then you can decide, make the word negative if you want when x is negative. What I want people to think about is the options here. You could do it for positive slope, rather than the actual x coordinate being positive, and what sort of expression you might need. And you can have that running in a maths application. All you need to do is, if you're measuring the gradient of the function, in fact, let's do it now. We've got 3 minutes left. Put in a notes application, and let's say in a math box. So we want, let's say, g to be equal to the derivative. And what are we doing? f1 of x? No, not g of x, just g. G is going to be equal to the derivative of, I think it's f1 of x, and given x equals a. That's it. So now go back to our thing, and let's change the conditions for positive, because we could write positive slope or whatever, and do g greater than 0 and see if we got that right. So we've got a positive gradient, yep, and now it disappears. So then you can put in a condition for negative gradient. And it's interesting because then the kids are really having to concentrate. So what's positive and what's negative? So they can see the function's positive, but all of a sudden it swaps over to negative, even though the function's positive. Well, of course, it's because the gradient is negative. And you could even pose the question to students without telling them. If you gave them this document and said, what is this positive and negative referring to? What is it telling us? And hopefully we get students giving answers like, oh, it's going uphill or downhill, depending on whether it's positive or negative. So not even telling them what it's measuring, ask them to figure it out. So a few extras thrown in for you. Well done, James, for being able to manipulate all my waffle in there and integrate it.
Great suggestions, Peter.
Yeah. So we are about out of time. Thanks, everyone, for participating in the chat. Let me see if I can just get back to my screen. Thanks, everyone, for joining us this evening. You will get a link to a certificate via email and also a link to James's documents that he's created. That was the file that we created or had. We'll see if we can get that out to everyone as well. And finally, if you want to see more of this sort of resource, it's available from our website, education.ti.com. Just put in a /Australia. It's not case sensitive, that's fine. And a bit of a wrap for next week's session. I'm not sure whether people have seen these images before. That one's a beautiful picture of a dinosaur, and then there's a lovely cross. And interestingly enough, the mean and I believe the median and the standard deviation of those data sets are identical, which I think is kind of cool. And so too is that one. And so too is that one. So if you were measuring anything to do with those statistically, such as the mean, the median, or the standard deviation, you get exactly the same answer from all 4 data sets. So just proves why we need these visualizations, because clearly there's not a lot of correlation going on between them. And that's in statistics in HSC mathematics. So if you know any people up in New South Wales that are teaching HSC, we're looking at stats, and we're using the TI-30X Plus Math Print Calculator. And I think we're all done for this evening. So thank you, James, and thank you, everyone, for joining us. That's all.